Today I'm going to do an experiment in which we heat some substances up and keep track of the energy added and some other quantities so we can start to build a quantitative model for how to know how much energy it takes to cause changes in E therm. This is our first attempt to actually put some numbers to energy. So in this experiment, what we're going to do is we have some water, 200 grams of water, and it's on a hot plate, and the setting on this hot plate is an 8, and that's going to turn out to be important because that's how we're going to, in a way, measure how much energy is being added to the water. Right now, the temperature is at 26 degrees. It's going to rise, and then as the temperature rises, we're going to, when it hits 30 degrees, start our timer, and then we'll see what happens then. So now the temperature is going up, approaching 30. You can see the hot plate there with the water inside it. And just as I hit 30, I'm going to restart the timer. So the time is at 0 seconds and counting. You can see the temperature is rising. I'm going to stop here and just make a little table and record some information. So putting down that we have water, 200 grams, and I'm going to make a table. On one column I'm going to put the temperature in degrees Celsius, and the second column I'm going to put the time in seconds. So we saw that 30 degrees C was at 0 seconds. Then we're going to heat it up 15 degrees to 45, and then 15 more degrees to 60, and see how much time it takes. So now we're in sped up mode. Time is happening really fast, and we're approaching 45 degrees, and now we're slowing down as we get right close to 45, and we're there. So now we're going to add 81 seconds to our table at 45 degrees, and then back to heating up again, and then speeding up time because it's boring to watch water heat up until we hit about 60, and now we're close to 60 degrees, and there we are, we're at 60 degrees. So we record that in 165 seconds. What we notice is it took 81 seconds to raise the temperature 15 degrees, and it took 84 seconds to raise it the next 15 degrees. So if you look at the overall change, it was just about double to heat it twice as much. So that gives us an indication that those two are proportional to each other. Now we're going to use 400 grams of water, same heater setting, and the same basic experiment. So starting out this table here, water, it's at 400 degrees, or 400 grams, or sorry. Build another table with Celsius temperature and time in seconds, and we're going to track it at the same three temperatures, a 15-degree rise and then a 30-degree rise overall. So the timer has started, and we're at 30 degrees and counting, and it's heating up. We're speeding time up again until we hit 45 degrees. Now as we approach 45, we're going to slow time down to regular speed. And there we are. So we record this 156 seconds to raise 400 grams of water by 15 degrees. And then we begin to warm it again. And again, we're going to speed up time. Until we approach 60 degrees. And now we get close to 60 degrees, we slow it back down, And right there, we've crossed the line. So now 321 seconds was how long it took. So the first 15 degrees took 156 seconds. The second 15 degrees took 165 seconds, so not exactly the same, but pretty close. So we can see that raising the temperature, the amount of temperature increase that you're going to require is going to be proportional, directly proportional to how much time it's going to take. And time equates to energy here because we're at the same hot plate setting. The other thing that we see is it's also proportional to mass, because when we doubled the mass, we also had to double the time. Now we're going to do the experiment again, only we're going to use a different substance, antifreeze. We're using 400 grams, so it's the same as the last experiment of water, except it's now a different substance. And we're going to see if all substances behave about the same or what. So same experiment, time, and then 15-degree temperature increments. So it just hit 30, I've started the timer, and there you can see my antifreeze, it's heating up. We'll do the same thing, speed it up until we hit 45 degrees. And there's 45. It took 90 seconds to get to 45. Now we continue to heat up. And then as we approach 60 seconds, or 60 degrees, we'll slow the time back down. And there it is. So it's 192 seconds. Once again, we see that the approximate time that it took to raise the temperature 15 degrees was the same. So that means that doubling the amount of temperature change doubled the time. And we also see that there's a difference between how much energy it takes to raise the temperature of antifreeze compared with water. It takes much less energy to raise antifreeze's temperature. So it depends on how much substance, how much mass, and how much temperature change. Three things. So what is the stuff, what is the temperature change, and what is the mass? So we can put this all together in this predictive model. Q, the energy that you have to add through heating to make the change happen, depends on three factors. One of them we saw is mass. Double the mass, we had to double the time, so it's directly proportional. The second one that we're going to consider is the temperature change. When we doubled the temperature change, we had to double the amount of time that it took, which means double the energy. And then the third quantity we're going to handle with proportionality. So we can make this into an equation. This is just a constant that you can discover by experiment called C. And the name for C is the heat capacity, or technically the specific heat capacity. We just say heat capacity for short. And this is unique to every substance. Obviously, water and antifreeze have a different heat capacity because we got different results for the same energy added to the same mass. So now let's summarize quantifying changes in thermal energy storage. One of the things that we found out that E-therm changes depend on is the temperature change. We saw that when we doubled the amount of temperature change, we had to double the amount of energy that was added because we had to double the time with the same heater plate or hot plate setting. So when we double the temperature change, we had to double the energy flow. That means that they're directly proportional. That's what that little funny symbol in between the Q for heating and delta T for change in temperature means. They're directly proportional. Whatever you do to one, you have to do to the other. So to double the temperature change, you have to add double the energy through heating. Another thing that we saw is it depends on mass. When we doubled the amount of water with the same heat setting and the same temperature change, we had to double the time. So that means when you double the mass, you have to double the energy flow. So they're directly proportional to each other as well. So we put these two factors together. That means that the amount of energy that has to be added through heating is going to be proportional to the product of the mass, how much is there, and the temperature change. But we also saw that it depends on the substance. We found that antifreeze and water didn't behave the same way. So how we handle that is we use this quantity called heat capacity. Heat capacity is different for each substance. Every substance has their own ability to modify how much the temperature goes up when energy is added through heating. So when you put all three of these factors together, you have a predictive model. You can weigh masses, you can measure temperature changes with a thermometer or a temperature probe, and then you can look up the heat capacity for different substances. Here's something interesting. This is a chart that I have here that just includes the result from our experiment in the middle column. It took 321 seconds for 30-degree change in water's temperature. It took 192 seconds for the same temperature change in the same mass of antifreeze. That was 400 grams in both cases. The time is proportional to how much energy was added because the hot plate was on the same setting, so it was delivering the same amount of energy in every unit of time. On the right column, I have the specific heat capacity, and this is measured in joules, that's an energy unit, for every gram and every degree C. So for water, it takes 4.18 joules of energy to make a gram of water go up by 1 degree C. For antifreeze, it takes 2.43 joules of energy for the same change in the same mass. Now let's look at some ratios here. I'm going to shrink this chart down to the left-hand side and make room for some arithmetic. When I take the ratio of the energy change, which is really the time change here, for water over antifreeze, I get a ratio of 1.67. When I take the ratio of the heat capacities, 4.18 over 2.43, I get 1.72, which is almost exactly the same ratio. So we can think about heat capacity as an ability to resist temperature change. Let's look at a problem that you might be able to use this new model to solve. This question says, how much energy is needed to cause 150 grams of water to warm up from 25 degrees C to 100 degrees C? I like to start these problems by doing a heating curve or cooling curve, depending on the situation, just to help me figure out which equation should I be using, because we're going to get another equation later on. And to model this, I've got a 25 starting temperature, a 100 ending temperature, and this is just a change in E therm. I can model this with my LOL chart. At the beginning, I have some E therm and some E phase. At the end, I have more E therm, but the same E phase because it's still liquid water. To make that change, I had to add some energy from my hot plate, and the question is, how much energy would it take to do that? Since this is only a change in E therm, the quantitative model that we can use here is that the heat energy added through heating, I should say, is equal to the specific heat capacity times the mass times the change in temperature. So now let's put some numbers to this. For water, 4.18 joules for every gram for every degree C is the heat capacity. We had 150 grams, so that's the mass. And from 25 to 100 degrees C, that's 75 degrees C, so that gives us our delta T. And when we do our arithmetic, grams and degrees C are going to drop out. Joules are the only unit we're going to have, which is good because heat energy, or energy added through heating, is an energy unit. And so we end up with 47,000 joules. A joule is a pretty small unit of energy, and so often these numbers are going to be quite large. So that gives you a reason to believe that this is a good model. We had an experiment that seems to back it up, and now we have an example of how it can be used.